right? In here, basically, we're going to discuss about same linear regression, but for multivariate linear regression, right? That basically means previously we have only one variable, right? So that is GPA, right? But now we have a set of features or the dimensions, right? Age, gender, awards, projects, uh, club member, union member, like that. We have set of uh, dimensions or the features for one particular data point, right? Suppose this is this one for some member like Nimal, right? So this is Nimal's data point, right? On that we have set of dimensions, right? In here, basically we consider the age, gender, program, GPA, like that. We have set of dimensions that are we going to consider for one particular data point, right? Previously we have only GPA, right? That's the main difference, right? So then, so this is also the convex function, right? So it's come up with the something like this, right? So basically gives an minimum, right? So on that case, we can basically, so our cost function has a minimum value. That basically means we can come up with the hypothesis that will fit to our data points, right? Fit means like most fitted. There is a most fitted hypothesis for our data points, right? So as we discussed before, right, the gradient is an algorithm, right? So the same theory is here, right? So if we need, so in here basically we need to come to a place like this, right? So this is the place where it gives the minimum uh, cost, right? So this is our cost function J, right? So this is the point where it gives the minimum cost, right? To come to that place, we need to, so we are basically using the gradient descent approach, right? There are some other mathematical approaches as well that are we going to discuss on this lecture, right? In the gradient descent algorithm, we already discussed, right? So we're going to update this theta, right, based on the portion of our derivation, right? So we basically derivate our cost function, right? So at this point, we derivate the cost function. So it will give some value, suppose like 5 or something like that, right? Then, so this alpha is the learning rate. So this is between 0 and 1, right? By using this alpha, right, you can set your alpha into something like point 5 or point. So in this case, we can use kind of 0.5 or something like that, right? By using these values, we're going to update the theta, right? So by updating the theta, so this is our new theta, right? So like that, basically it will go on this kind of a pattern, right? So if you're familiar with the derivation, right? So if we derivate some function and it will become zero at a maximum or a minimum, right? In this case, we have a minimum, right? So this is our minimum value, right? So if we keep updating the theta, right, at this point, our derivative becomes zero, right? In that case, if we try to update the theta, so the derivation becomes zero, theta going to converge to some value, right? So now the theta updating process stopped or the converge, right? Why? Because at this point, our derivation is zero. Because of that, if we subtract some portion, subtract zero out of some value, that basically gives the same value, right? So now the theta going to converge, right? That's why it will give the some, it will give the minimum cost function, minimum value at this point, right, for a particular theta, right? So we keep updating the theta, right? For each particular point, we derive the cost function, right? At this point, we know in the mathematics, so the derivation becomes 0. In that case, if we try to update the theta, right? So alpha times 0, it will give 0. So the theta stopped updating and it's converged, right? At this point, it will give the minimum cost value, right, with set of parameters, right? By at this point, our hypothesis basically will be the most fitted hypothesis for our training data, right? That's the basic idea. So it's will go in this kind of a pattern and come to a place like this, right? So, so the same theories we going to use, right? So, but the different is, so in here we have multivariate data points. That means it have set of data points like previously we have only GPN. Now we have age, gender, like that. We have set of dimensions, right? If you consider one particular data point, right, it has set of dimension, right? So if you consider X as our input, that is a multivariate data point. That means it has set of dimensions, right? So again, it's a kind of a vector, right? Previously, it's kind of one value, but now we can consider it as a vector. Vector means, like something like this. So if we consider our, suppose, 0 data point, right? It's something like x0, 0, x01, x02, x03, like that, up until x0d, right? In this case, we consider we have the number of features of the dimensions, right? Then, so this is xi mean basically the ith data point. So this is the 0 data point. If we consider the ith data point, xi0, xi1, xi2, so xi3, like that. Let's go up until xid. So this is the ith data point, right? So if we consider this is the kth feature of ith data point, right? So these are the features or the dimensions, and these are the data point, right? So it's starting from x00, x01, x02, x0d, right? So this is 0. Then if you consider 100, right, x100, x101, x102, then x100d, right? So this is how we write our data point, right? So basically you have to keep in mind, in this case, we have a vector, we are dealing with the vectors, right? So we have d plus 1 dimensions, right? So maximum dimension number is d, right? Then, so we have d plus 1 here. Then, if you consider we have n number of data points, then we have n number of data items, right? That basically means xn 0, xn 1, xn 2, xnd, right? So this is the nth data point, right? So by this we gives the data point, and with the power we gives the dimensions, Right. Then, in univariate linear regression, this was our hypothesis, right? So it has only one value so it has only one value like GPA. That because of that, we have only one X here, right? But if you consider the multivariate linear regression, right? Now we have the number of dimensions, right? If we have the number of dimension, we should come up with the number of parameters as well, theta parameters, right? So in here we have, it's kind of the same, but it's complex because of the additional dimensions, right? So this is the same as the univariate linear regression, right? Additionally, we have theta 2x2, theta 3x3, go up until theta dxd, right? In here we have d plus 1 theta parameters and d plus 1 x as well, right? So the maximum value is d, right? So to make it more convenient, so we can basically come up a place like this. We can, so this is if we have theta naught, right? So if theta naught times 1, basically we can write it theta naught as this, right? So like the power 0 power of any number that gives 1, right? So we can write something for this theta naught like this, right? So now for convenience, we can change this into theta naught times x naught, right? X to the power 0, right? So theta naught, theta 0 x 0, theta 1 x1, theta 2 x2, like that. We can basically come up to a place like this, right? So previously we have only one variable, right? Then in the multivariate, we have the number of dimensions. In here, we have only one dimension, but here we have the dimensions, right? To cope with that, we should come up with the number of same number of parameters as well, right? To learn the cost function, right? To make it more convenient, we put another x to the power 0 here, right? Now we have something like this, right? So basically in the future, we can write this equation in kind of a summation, right? So because it's starting from 0 and go up until d, that's why we put another x naught here to make it more convenient. So as I said before, so this data points are kind of in vectors, right? So here it's starting from x naught to go to xd, right? So this is our vector of x. Then this is our parameter vector, right? So this is the equation we have for our hypothesis, right? So we can make it more simpler by writing in this form, right? So these are in vectors, x and theta, right? So if you transpose this theta, you can come up with something like theta naught, theta 1, theta 2, theta d, right? So then you can multiply it with the x, right? X is another vector, right? So if you're not familiar with the vectors, that is, you can basically get some basic idea of the vectors, right? So in here, so you should focus on some theoretical aspects, not the mathematical equations or the mathematical aspects, right? So if you are not familiar with the mathematical aspects, that are kind of okay, right? Just focus on the theoretical things, right? So make it more simpler, we can write it as theta transpose. Transpose mean like rotating this vector, right? So in here we have something like this, then we transpose it into something like this, right? So now we can write this equation, so the same equation as theta transpose x, right? So it's kind of to make it more simpler, right? So we started from here, right? We add another x naught here, x to the power 0. Then, since these are in vector forms, in vectors, because of that, we can make it more simpler by using, write it as theta transpose x, right? So if we multiply this, this will basically give this previous equation. So now we have the cost function, right? So this is our cost function, right? So this is our hypothesis value, and this is our actual value, right? So now we can basically uh, make it more. Basically, we can right. So in here, basically, now we have our cost function, right? Theta transpose x, right? So we can simply make it like write in form of theta, right? So now we can write the hypothesis in this form, right? So theta transpose xi, right? So this is our hypothesis. We can simply replace it with the previous simpler form, theta transpose x, right? So then we can remove this hxi, right? Then we can write it in vector form, theta transpose xi, right? The same thing, right? So this was the cost function, right? For the multivariate, so we can replace it with something like this, right? So we simply replace this hxi with our theta transpose xi, right? So then, so we have to, we basically using the gradient descent approach, right? So in gradient descent approach, we have to derive the cost function, right? Then update your thetas, right? That's the basic idea, right? It's applied here as well, right? You can do the partial derivatives and update the theta node, theta 1, and until theta d, right? So after you partial derive the cost function, you end up in some value like this, right? So if you derive this cost function from theta naught, so this will give something like this, right? So I'm not going into discuss the mathematical aspects since you are not coming from the mathematical base, right? So I'm just give some surface idea, right? So then if we derive the cost function from theta 1, this will give something like this, and finally, so it's end up in xd, right? If we derive from theta d, then it will come to place like this, right? So then if we update all our theta values, right, we have now d number of thetas, right? Previously we have only theta 0 and theta 1 in the univariate, right? But now we have started from theta node, then we have go to until theta d, right? We have, suppose if we have 100 features, then you should update 100 parameters as well, right? So you have to do this until it's converged, right? So Yeah. Then, so with the, so this cost will be basically uh, come to a convergence like this, right? So when you are updating the thetas, right? So so our cost function basically start to minimize and kind of a converge to some level, right? So you can see this error is getting, so this is the error. So this error function, it's getting reduced, right? You can see starting from very high and getting reduced, right? So this is the convergence with the theta, right? So we discussed these things in the previous lecture, how how the cost function getting reduced, then how the hypothesis change and fit with the data points, right? We discussed these things, right? So, so the gradient descent approach is a kind of iterative process, right? You have to update, you have to keep updating the parameters, right? Until the parameters getting converged, right? So this is the iterative process. Then there's another method called normal equations, right? That's kind of a straightforward thing. You have to simply derive the derivate the cost function, then find the values, right? So, so in here we don't need to come up with any gradient descent approach, right? You can simply derive the your equation, right? As I said before, if you if you have a cost function something like this, right? So if you derive this, so the theory is it will become zero at the maximum. So in this case, minimum, maximum or in the minimum, right? So if your parameters are, if your features are less, right? In that case, you can simply do the derivation and find the place where it gives the minimum value, right? So to do that, you have to get the partial derivatives because you have theta d plus one number of thetas, right? That means you started from theta naught to theta d, you have this number of parameters, right? So suppose this number is like 1 million or something like that. So, no, like 10,000 or something like that, right? In this kind of scenarios, the normal equation method is not going to be effective, right? So it's kind of computationally costly, right? But if we have something like 10 or 100 or something like that, these kind of scenarios, this will be much easier, right? It's kind of gives the value directly, right? You don't need to follow any iterative approach, right? You can simply get the partial derivatives and make it equals to zero, right? At that point, you can get uh, the theta where it gives the minimum value, right? So in here we have to, so you can't simply derive the this kind of thing, right? Because it's a function of theta zero, theta one, and go until theta d, right? Because of that, you have to take the partial derivatives and make it equals to zero, right? So if the features of the dimensions are higher, this is not effective. But if the features are or the dimensions are less, and this will be a good approach, right? Since you don't need to follow iterative approach, right? So, so now we're going to do this in the normal equation method, right? So now we finally end up in this kind of equation, right? So this is our cost function. So previously it was hxi, then we replace it with theta transpose xi, right? Then if we can come to a place like this, x into theta minus y, right? So that will be more like mathematically when you are deriving when you are derivating the cost function, that will be more simpler, right? So this is the place where we going to approach, right? So these two, this basically means the norm, right? So x theta minus y, by using these two lines, that basically means the norm. We are getting only the value, right? So if you are familiar with the vectors, right? For vectors, we can find the value of that vector by using the norm, right? So now we're going to approach from this and come to this place, right? So first thing first, right? You can write this in this kind of method, right? This kind of form of the method, right? So in here, that this is basically we started from I equals 1 and go up until nth data point, right? So you can write it in the expanded way, right? Theta transpose x1 minus y1, right? Then we get the square of that. Then the second one, theta transpose x2 minus y2. Then we get the square of that, right? Like that, we can expand this equation, right? So this is the summation starting from 1, go until nth data point, right? Don't worry about this n, it's a scalar value, right? So the scalar is not going to affect when you are dealing with this kind of scenario, right? Then we can basically sub these values, right? Now it's x1 transpose theta minus y1. Then we take the power of 2, right? Then x2 transpose x2 transpose theta, then minus y2. Like that, you can make it write it in another form like this, right? You will see why we going to need this kind of form, because we need to approach x theta minus y, right? So the first value is x, the second value is theta, right? That's why we sub the two values, right? So both are the same same dimensions, right? Then we are getting the square of that, right? Then right now we are in this place, right? Then so if we consider this x and theta, right? So so here we have x1 transpose, x2 transpose, xn transpose like this, right? Then we have theta 1, theta 2, theta d, right? So here you can see it's basically here, right? So x1 transpose theta t, x2 transpose theta, so xn transpose theta. Like that, we have that here, right? Then we can simply come up with some equation, right? So like x, if you consider the matrix x, that's in it has a number of rows and the number of columns, right? So we started from So in here we have 1, and here we have n, right? 1, 2, 3, 4, like that. We have n number of data points and d number of dimensions. For one particular row, if you consider this row, we have d number of columns, right? So if you consider this matrix X, that's in n by d matrix, right? Then if you consider this theta, it's in d1, right? So we have d number of rows and 1 column, right? If we multiply this, basically gives n. So this is in d multiply with d1. This is going to remove, and basically it's given n times 1 vector, right? So it has, if you multiply this, if you're familiar with the vector multiplication, you can simply do that, and you will basically end up in some place like here, right? So it's basically give the final output as x1 transpose theta, x2 transpose theta, and go until xn transpose theta. It's starting from 1, 2, 3, like that. This is the nth data point. So the output will be in n by 1, right? So now we're going to approach this x theta y, right? Now we have this x theta here, right? We get that. Then you need to subtract y, right? So you can simply write it as here, right? So here we have the x theta, right? And you can subtract each y1 data points, right? So this is y1, y2, y3, like that, go up until yn, right? So if you write it, if you subtract it, you can simply write it as this, right? So in here we have, for first data point, you get the transpose and multiply with your set of thetas, then subtract by y1, right? This is basically gives the error, right? So for the generic one is here, it is x theta y, right? Now we finally want something like this, right? So we started from hx iyi, no, right? Then we replace it with x transpose theta, right? So we have, right? Now we need to come up with a more simpler form, right? So this is what we want, right? So, but we have this one, x theta minus y, right? So this is a vector, right? So you can see, if you get the norm of this vector, this one, that you can see. So this is basically getting squared, right? Taking the norm, right? Suppose ABC, right? If we take the, suppose this is k vector, right? So if we take the norm of this vector, that basically gives a squared, b squared, c squared, and it get the power of half, right? So this is the how we get the norm, right? Now we have the values. You can see, if you get the norm, right, then we can approach our final statement, right? Final equation, right? So now we're going to take the norm of our equation, right? So that will gives x1 transpose theta minus y1. Then we get the power, of 2, right? Like that, then we have x2 theta, x2 transpose theta minus y2, then the power of 2, right? Like that, if you take the norm, now we are finally come to our expected equation, right? But still we have uh, this one, right? We need to remove that. To remove that, we can basically make it norm square, right? So we get the norm, then we take the square, then this will be uh, removed, right? Now, finally, we are end up in our final statement, right? So now our cost function is updated to a place like this. Now we have x theta minus y, and we get the norm of that vector and make it square, right? Now it's only in as a function of theta, right? Now, what we're going to do is, now we know the cost function, right? Then if we derive this cost function and make it equals to 0, at that point, we get the needed parameters, right? You can basically derive this cost function, right? So delta means the derivation, right? So delta j theta. So if we derive this, so that will give something like this. So n is a scalar, we can remove that. Then we end up in some place like this, right? So if you multiply this x transpose x theta and x transpose y, right? Then we can simply move this x transpose y into the other side of the equation. You can basically uh, cut this x transpose with x transpose, right? So why? Because it can be either it can be 0, right? So you can simply cut it from the both side if it is not equal to 0. But in this case, you cannot do that, right? So now you end up in some place like this: x transpose x theta equals x transpose y, right? So what we are doing is basically uh, do the normal equation, right? So we did the normal equation here. We get a function and basically derive that, right? To make it more simpler, that's why we started from hxi minus yi, that basic cost function. Then we start to derive set of equations, and finally we will end up in this place, right? So then we can basically derive this directly, right? Then we can come to a much simpler form like this, right? So these mathematical things will not much familiar with you, right? So don't worry about that, right? Just keep in mind like this derivation, if we make it derivate and make it equal to 0, that gives the needed parameter, right? That's the only theory here, right? Now we need to find the set of parameters, right? We need to find this theta. To get this theta, so these are in vectors. You can multiply this whole thing with x transpose x, the inverse of that. So we have this inverse, right? We're going to multiply the both side of the equation by x transpose x, and we get the inverse, right? With that, we can remove this part, right? So if we remove this x transpose x, if we remove this part, that basically gives the set of parameters, right? You need only the parameters, right? To get that, you can simply multiply the both side with the inverse, right? If we multiply with the inverse of this, that basically gives the identity matrix. that the basic idea is it's like 1, right? The number 1, right? If you are multiply something with the identity matrix, that gives the same matrix, right? So now we're going to multiply it with the X transpose X inverse, right? So that will basically remove our X transpose X part. Then additionally it will add this X transpose X inverse to the other side, right? But in the left side we have the only the theta, right? So I is the identity matrix. If we multiply anything with the identity matrix, that will give the same matrix, right? Now we can have the theta here, right? On the right side we have X transpose X inverse, then it's multiplied with X transpose Y, right? If you know these values, basically you know the values, right? Then simply you can find the parameters, right? So we call this part X transpose X inverse into X transpose, the whole thing, as the pseudo inverse of X, right? It's just the name, right? So we call this as the pseudo inverse, right? Then here we have the Y. You know Y, the actual value, right? So you can basically construct your X matrix from the training data, right? Then you can construct the vector Y, right? You know the labels of the data, right? Then you can compute the pseudo inverse out of this X, right? You basically create the matrix X here, right? Then you can derive the pseudo inverse. You know the Y, right? Then you can simply end up in this place. You can simply find the parameters, right? The parameter that will gives the minimum cost function. So minimum value out of the cost function, right? So this is the pseudo inverse, right? First you compute the matrix X, then you transpose this, transport the X, then multiply with X again, then take the inverse. That value you can simply multiply again with X transpose, right? That's we call it as pseudo inverse, right? Then you know the actual value of Y, the actual label or the class, right? Then you can multiply the whole thing and compute this equation and finally end up in finding the parameters, right? So this is the normal equation method, right? There are no any gradient descent approach, right? So if we have a less number of dimensions in this kind of scenario, you can basically use the normal equation method, right? If we increase in the dimensions, so this will be computationally heavy, right? In that case, you can simply go for the finding the gradient descent approach, right? You can go to the gradient descent approach and find the parameters, right? So that's the basic idea of normal equation method. Then, yeah, if we consider this gradient descent approach with the normal equation, right? So in gradient descent, we have a learning rate, alpha, right? So it's an iterative process. You keep updating the theta, right? You keep updating the theta until it's stopping updating or until it's converged, right? So the thing is, so if we are getting the inversion of the matrix, so these calculations basically computationally heavy, right? That's why this is not recommended for when we have a very larger features, right? If you have very large set of dimensions, in that kind of scenario, you can't use the normal equation method, right? For that, you can go for this gradient descent approach. If not, you can basically go for normal equation method, right? Basically, you are basically getting the partial derivatives and make it equals to 0, right? So what we did was we started from hxi minus yi, then we can start derive set of equations, and finally we end up in one particular point. If you know the matrix X, then you can compute the pseudo inverse of that. You know the Y, right? Then you can compute pseudo inverse of X and Y. Then you can simply find the set of parameters, right? This is just the two different approaches, right? Okay. Now we're going to discuss about the logistic regression. Up to now, we discussed about univariate linear regression. That means we have one variable, like only the GPA, right? So that is basically we can use the so basically we can use the gradient descent approach, right? So if you have like a multivariate linear regression, that means if you have set of dimensions, so that you can either use the gradient descent approach, or you can go for the normal equation. You can use the normal equation for the univariate regression as well, right? So now we're going to discuss about logistic regression. Logistic basically means it's not gives an continuous numbers, right? If you can consider the linear regression, right? So that can give any number, right? 1, 2, 300, anything. But if you consider the logistic regression, it has only set of classes, right? Set of defined values, right? So in our basic linear regression, our hypothesis, we can write it as this, no, right? Theta transpose X, right? So that basically gives an real value, right? So any number like 100, 1, 2, any number, right? So, but we are come to a like a classification problem, right? Suppose you have two classes, like the with some like if you consider example like healthy cells and the cancer cells, like that. If you have two classes, right? If you have only two classes, in that kind of scenario, you can't basically use the linear regression, right? So that's not the correct approach, right? So you know that our linear regression gives the any real value, right? But in classification problem, you have two classes. It can be 0 or 1, right? -1, +1, right? Like that, you can have set of classes, right? For that, you have to apply another sort of function to reduce this real value into our expected value, right? So the linear regression basically does not suit for the classification problems, right? For that, we have to go for a logistic approach, right? So, so our hypothesis need to restrict into suppose 0 and 1, right? In this case, so our hypothesis should be within 0 and 1, right? So to do that, you can come up with the restrictive function called gx, right? So hx is our linear regression hypothesis. Then uh, we are using another function called restrictive function. Then in the this hx basically include in our restrictive function, right? This restrictive function makes sure the output value will be within 0 and 1, right? So we can call this G as our logistic function. That is basically gives a logical value, 0, 1, something like that, right? So this our linear regression gives an real value, right? We need to restrict the value into predefined range, like 0 or 1, right? To do that, we can apply that. We can apply our restrictive function top of our hx, our linear regression, right? So that's the basic idea, right? So this is just one function. We call it as sigmoid function, right? So this is the sigmoid function. You can see, right? If I keep increasing the value, right? Right. If you keep increasing the value, you can see this function basically converges into 1, right? Then if I go to the negative infinity like this, you can see this function converges to 0. This is the 0, right? Now you can see, so if we apply any number, right? This is make sure, so the output value will be either within 1 or within 0, right? So this is restricted, right? So this is basically restricted on 0 and 1, right? So if we apply any value, but our logistic function makes sure, okay, if you put like 10,000 or something like that, but it will give the output value as 1, right? Right, clear? So this is just one instance of a logistic function. This is sigmoid function. This is the sigmoid function, right? So this is our sigmoid function here, right? From the linear regression, we end up in some place like theta transpose x, right? So this is our linear regression function. This is our restrictive function, right? So we need to apply our restrictive function on top of our linear regression, right? To do that, we need to simply replace these x values with this theta transpose x, right? So that's basically in the mathematics, right? So in here we replacing x out of this theta transpose x, right? So our final function will be look like this, right? So we replace this x with theta transpose x. Now we have here the theta transpose x, right? So this is the final function, right? So we need to fit our theta parameters for this function, right? So then suppose this kind of a scenario, right? So this is our function, right? So this will give something like 0.82, right? So you know the sigmoid function, right? This will go like this now, right? Suppose this is 0.5, right? So if something within 0.5 and 1, we can put it in class 1, right? So right, so this is 1, this is 0, and this is 0.5, right? So our function basically gives us 0.82. That's something, some place like here. Some place like this, 0.82, right? So we can use the threshold value as 0.5, right? So now it's beyond the 0.5. Then we can simply put this as class 1, right? Another form, if you take the probability, right, you can tell that it has 82% probability to fall under class 1, right? In the other word, that basically means it has 18% probability to fall that this value under class 0, right? You can see, so it has more probability that will fall under class 1, right? That's the basic idea, right? So if we assume our logistic regression hypothesis as H naught, right? So this is our function, right? So this G naught is our linear regression hypothesis, right? So you know it started from theta naught and let's go until theta d, right? In this case, we have theta 2, right? So this is our linear regression hypothesis, right? So you can see, so if we, according to the sigmoid function, right? If we, right, so, so this is our logistic regression function, right? Then this is our linear regression function, right? So this is our sigmoid, right? So we apply our linear regression. So if we consider this sigmoid function, right, you can see, right, anything that's positive, right? So that basically gives fall under here, right? If something gives negative, that means less than 0, that's in this area, right? So, so this is our value that will gives by the our linear regression, right? So it can be theta naught plus theta 1x or like that, right? So you can see if this linear regression gives a positive value, right, then the output will be 1, right? Because so the function is here, right? Then if our linear regression hypothesis uh, give something negative or the less than 0, right? Here you can see, so that will fall under class 0, right? You can see the function, segment function behave like this, right? Then you can come up with the decision boundary, right? So if your linear regression gives something positive, right? Positive value, so that's fall under 1. If it's give negative value, that's fall under 0, right? So this will give class 1, this will give class 0, right? So then you can write it as, so the decision boundary here, the 0, right? If our linear regression function, if our linear regression, if it is equal to 0, so that's the decision boundary, right? So you can see anything that positive fall under class 1, anything that negative fall under class 0, right? So this is our logistic regression. This is our linear regression hypothesis, right? We apply that on, we apply the sigmoid on our linear regression, right? So that will restrict into the output value within 0 and 1, right? As the decision boundary, we can take our linear regression equals to 0, right? Then when you're dealing with the cost function, right? So we need to fit the training data points, right? And reduce the cost and make it more fitted to the training data, right? When you're considering the linear regression, so our cost function was this, right? Hxi minus yi, right? But so in the linear regression, you can have any real value, right? But in the logistic regression, we have we're going to do some classification, right? We have some defined value, either 0, 1, or minus 1, 1, 0, 1, 2, something like that, right? If you use this cost function, this one, to train our parameters, right? So we will end up in some kind of a local minimum, right? The meaning is, if we are use cost function, this cost function for classification problem, right? So the cost function will look like this, right? That's not kind of not a convex, right? Because of that, right? You can't use this cost function to deal with when you are dealing with the classification problem, right? So we need to come up with another approach, right? So this is our sigmoid function, right? You can see, so we can write our cost function like this, right? So it's a function of h theta xi and yi, right? So what I mean by this cost function is defined here, right? If our class or our label is equals to 1, we can use minus log of h naught x, right? If our class is 0, right, then you can replace this h naught x by 1 minus h naught x, right? That basically mirroring the log function, right? So why? Because this it has this minus the negative value here, right? Because of that's getting mirrored, right? I'll show you what will happen, right? So if you are consider the final cost function, you can write something like this. If you are look at this cost function, you can see here we have one portion and here we have another portion, right? If our y equals to 1, right, in that case the whole thing will be 0, right? So 1 minus 1, that basically gives 0. If you multiply anything with 0, that's give 0, right? So only the affecting part is portion is this, right? If our if our class is 0, right, in that case, so this y becomes 0, then the whole thing becomes 0. So only the effective part is here, right? So here the mirroring thing, right? So this is our minus log hx, right? And these are minus log 1 minus hx, right? As you can see, that's basically mirror the function, right? Then if you can see this, right? So if the right, so here we have our class 0 and 1, right? So if our y is equals to 1, right? If our y is equals to 1, so we should consider only this, right? Minus log hx. That means this one, right? So that is this, right? You can see if our y equals to 1, you can see our cost function getting reduced, right? So if it's hit the 1, in that case, the cost will be 0, right? Nearly 0, right? Then if our y equals to 0, right? If our y equals to 0, in that case, we should consider this function, right? So why is that function? So we have that function here, right? So this is that function, right? If our y equals to 0, right? As you can see, if the y becomes getting equal to 0, you can see the cost function getting reduced and come to the 0 point, right? So the other word, if our y equals to 1 and our hypothesis give it as 0, you can see, so the cost will be huge, right? Right? Suppose our uh, hypothesis gives something like 0.1 or something like that, right? That's very near to 0 in that case. So cost function tells that, okay, now your cost is very high, right? So this is not the correct classification, right? Then if our y equals to 0, y equals to 0 means the actual class, right? So suppose this is cancer cell and this is healthy cell, right? So in the our data set, it's labeled as the cancer cell, right? But our hypothesis gives something near to 0.1, right? That means it's kind of near to a healthy cell, right? But that's triggered our cost function. That's basically tells that, okay, your prediction is incorrect. Why? Your cost is high, right? Your cost function basically give this much of cost. That basically means that's not the correct predict, right? So in the other word, if our uh, cell is considered as healthy cell, that means y equals to 0, right? So then in that kind of a scenario, your hypothesis give as 0.9. That means that's nearly a that predict as a nearly a cancer cell, right? In that case, that's notified in the cost function because now the cost is very high, right? If you go into the near to 1, now the cost getting higher, right? Because we are using this function, right? If y equals 0, we should consider this one, right? So now the cost is high. If our y equals to 1, we should consider this function, this log, right? This log function. So that is the basic idea. You have two log functions, right? So for particular classes, we are using two different log functions, right? If one log function gives, if y equals to 1, then if you go towards the 1 here, right? Now the cost will reduce, right? From other function, if you go towards 1, if our class is 0, right? In that case, that's incorrect, right? So that basically gives, okay, your prediction is not correct. Your cost function gives a higher value, right? That's how we're dealing with the logistic regression, right? So we have two different uh, functions, log functions for our two different classes, right? So as a whole, we can write the cost function like this, right? So for if y equals 1, this one will affect, and if y is equals 0, this one will affect, right? As a whole, you can write it like this. If y equals to 1, the whole thing becomes 0. If y equals to 0, the whole thing becomes 0. Right? Yeah, these are the some log functions, right? So if you're familiar with how the functions behave when you're coming to log, if we reverse this, if we reverse this in here, it's positive, right? But in here it's in -1. In that case, that will mirror in some arrays like this, right? So these are in the mathematics, right? Okay. So the final cost function, we can write it as this, right? Then if you take the summation, right, you can end up in some place like this, right? So you should consider each data elements, data items, right? Right, you can write it as yi log h naught xi, right? Plus you can take this minus out and write it as this, right? Then 1 minus yi log 1 minus h naught xi, right? You can take the mean out of that, right? So this is the final cost function for a logistic regression, right? So then you can simply derivate the cost function, right? So this was our cost function. You can derivate it, then you will end up in some place like this, right? Then you can update your thetas using the gradient descent approach, right? You can take the derivation and apply a learning rate, right? Then you can keep updating the theta, right? So you know the h naught xi, so that is this, the final value, right? That's basically this is in here we have the linear regression applied. In top of that, we applied the restrictive function. In this case, that is sigma, right? Here we have the h naught xi, and you know the yi, right? You can keep updating the thetas and until it's converged. You can do this iterative, right? So to minimize the cost, you should fit these parameters to get it out of minimum out of the cost function, right? So our minimum, this is our GT types, that is here, right? Then yeah, so basically we have in the logistic regression, we know why the linear regression is linear cost function is why it's working on the logistic regression, right? So in the class, we are going to do some classification problem. That means it has some defined class, right? To get that class, we need to apply a restrictive function. So one example is a sigmoid, right? Then we discuss about the decision boundaries. Then when you fit in our parameters, so the linear regression cost function is not going to work in this kind of scenario because our class is, it's a kind of a defined value, not a real value. So that will not give an convex. Because of that, we can't use the normal linear regression cost function, right? To deal with that, we come up with some two log functions, right? Then we discuss how those log functions work for two classes. Then we discuss the final cost function, right? Then we going to basically use the gradient descent approach and update our parameters, right? Then so we're going to basically minimize our cost function based on our so so in here we basically come up with the we can update our parameters until those are converge, right? So that's the basic idea of the logistic regression, right? So in here we basically you need to get the basic idea about so why we need two log functions, right? So how to deal with two classes, how to restrict the output, then top of that how to calculate the uh, how to calculate the parameter, like how to fit the parameters, right? So we started from the multivariate linear regression, and we did some mathematics, right? So it has the same kind of thing like the univariate linear regression, right? Then we discuss about the normal equation, right? We come up with some simpler form like this, right? Then we discuss how to get there by using the norm, right? We did some transpose and did some multiplications and end up in some place like this, right? Then so we did all those things to make it more simple and make it our calculation much simpler, right? So finally, if you know these pseudo inverse, right? In that case, you can simply multiply it with your class label, available label, and you can simply compute the parameters, right? That's a basic idea. Towards that, we did some calculations, right? If you're not familiar with the calculations, that are totally fine. You should have just the theoretical idea, so right? So that's the end of the lecture, right? So see you guys on next time.